Hey folks, so we're going to continue today thinking about some graph problems, but we're going to shift focuses a bit on the topics. Specifically, today I want to think about the existence of hard to solve problems that are in some way difficult. Um, so far in the semester, we've seen a bunch of algorithms just to solve these various problems, these really clever algorithms, and these runtimes of these algorithms, for the most part, have been polynomial in the input size. By that, I mean you get like big O of n to like a constant. All right, where C is a constant. Sometimes you'll alternatively see this written as n to the O1. So there's another way you can see this written. It's like n to the power of a constant. That's polynomial runtime. A question you might ask yourself at this point is, can most problems be solved within n to a constant runtime? Seems like the problems we've seen so far, we found ways to do it. But are there any problems that, say, require like a 2 to the n runtime or something like that? This is not polynomial, this is exponential. Okay? Make sense? So that's what I want to think about today. I guess you can start by just getting a guess in your mind. Are there problems that are not solvable in polynomial time? What would they look like if they did exist? How could we go about proving them? Good stuff to kind of think about for a moment here. And I have a little problem to think about to get us started. This is a somewhat famous problem, so you may have heard of it even, depending on what you watch or read, the traveling salesperson problem. So the traveling salesperson problem has an input of an undirected graph with weights on the edges. And the goal is to find the shortest tour, aka the term we used was cycle, that visits each of the vertices exactly once. So you want to find the cheapest path that does a round trip. Let me draw you an example of that. So let's say you're a traveling salesperson. Maybe this is where they live. Right? This is their place of residence. This is their base of operations. And then let's say all of these vertices I'm drawing, these are cities that they want to go and maybe do some door-to-door selling at. It's an older problem, right? A little bit antiquated. But so they want to go around between all these cities in their area and sell stuff. Okay, well, the cities have different costs to travel between. These costs, you could think of them like the cost of air travel, like to take a plane between them. Or maybe it's a cost of a bus, or maybe it's distances, right, in miles. That would also be, possible. So you could imagine something like, like this, say, and you could have more connections, right? You could add a connection like that or whatever. And then you can put a bunch of numbers associated with these edges. So, I don't know, just make up some numbers. Let's say this is 10, this is 20, this is 40, this is 5, this is 16, this is 35, this is 19. Yeah, so just whatever numbers you like here. 43, 50, 9, 11, 12, 15. Let's say, just keep the numbers more or less unique. And then, given this graph, we want to figure out what's the best path to take through it if we're trying to minimize our total cost of the path. So looking at it here, let's see. We could, let me get a color it shows up here. Let's say purple. We could go like here first. So the traveling salesperson travels from here to this city. And let's see, they could go here directly for 35, but maybe they see, oh, there's a cheaper path. They can go down to this city for 5, and then back up for 16. And then same deal, they can like take this direct route here, and then here. They can't revisit cities, remember, so they wouldn't take this route, even if that city were available at this point. They can't go back to a city. They only want to visit each city once. Okay, and so then take the 11. Let's see. Kind of don't have a choice here. We sort of have to take the 12 just based on how I've designed it. And that means we have to take the 28, and then we end up with the 20. Okay, so I don't know if that's the best possible route through this, but let's say it is. So if this is the shortest cycle, which visits each vertex exactly once, aka it's a simple cycle that visits every vertex in the graph. Okay. So given this simple cycle, we can calculate its total cost. Just add up all the numbers along it. You can think, is this, what's the total cost for this guy, and can you find a route that's better? Feel free to stare at it and see if you can figure out a better route. Okay. Oh, I do have one of these guys that's unlabeled. Oops. Let me give this guy a number. I'm going to cheat because I left it unlabeled. I'm going to give it a big number. You can think about this guy. You could draw your own graph. You could draw a very complex graph. It could be a graph that represents all the possible flights in the United States or something. All the possible routes you could take in the United States. It becomes a very big problem. And this is a very natural problem at the same end. It seems a lot like the problems we've been solving, like Dijkstra's algorithm, or these sorts of like minimum spanning tree problems, right? We're connecting all the things together, and we're trying to minimize some cost. Despite that, the best known algorithm to solve this guy takes n times 2 to the n time. Order n times 2 to the n time. Exponential time. That is not great. That is a very slow algorithm. And this is not necessarily an isolated problem. It turns out there's a lot of problems like this where we don't know a good way to solve them, or even if there is a good way to solve them. And they can kind of ambush you. If you don't know what these problems look like or how to spot them, if you're a software engineer, you might run into one of them without even realizing it, right? If you are someone trying to solve these problems and you're like, I'm going to write a program to solve it, and then you think you've solved it, and then you find out, no, actually, there's a bunch of cases I didn't think about, and my algorithm is not producing optimal results. All right? Maybe that's the problem. I got 2 numbers associated with this guy. So, thinking about this guy, I think it gets tricky because it's just, while it's a simple problem, we can do better. We can find an even simpler problem, this one. So I'm going to leave behind the traveling salesperson problem for the moment. We will revisit it in the future, though. Rest assured. And instead, we're going to think about another problem a simpler problem. Now, before we get into that, the problem of clique, let me just give you an idea of kind of where we're going high level. So you might think, seeing this problem, you're like, well, what can we do? The obvious thing is to just, sit around and try and design a better algorithm. You might be like, even right now, thinking about how would I solve that traveling salesperson problem? Maybe you're thinking about it, would be especially thinking about it if I told you there's like $1 million prize for solving these problems. So it would be worth money. So you might be thinking about this, might be thinking, how would I solve these problems? But what if people try, as they have for these problems, for decades to solve them and have no luck? Try for decades, brightest people in the field, have no luck. Well, given that, the next thing you might think about doing is like proving then that it's impossible. If people haven't found a solution to it, maybe it's because there is no solution. Makes sense. But, well, that would be great. It also seems difficult to prove. The best lower bounds that you can establish are not strong enough to show this. We did see cases where lower bounds were useful, but they tend to be really tough to prove. Yeah, really tough to prove. Okay. So those two kind of dead ending. Now the question becomes, what else is available to us? What else could we do? Well, let's try to identify maybe the problems that are hard. And in particular, can we prove maybe some sort of equivalence? Can we show that all of these problems are equal to each other in some way? Then, if one of them is solved, all of them are solved. It lets us combine research efforts. This is what we're interested in here. Okay? And I guess I can pull the veil back here. For people who know this term, what we're thinking about is the very famous problem of P versus NP. That's where we're going. Okay? P versus NP, these are complexity classes that are essentially doing what we're describing here. We'll think about them, though. We'll think about them quite a bit, but not today. Not in this set of notes, at least. All right? So, another difficult problem. Clique. This is a particular variant called the optimization variant. We'll think about a couple other variants in a moment, where we're given a graph with, of course, vertices and edges, another graph problem, and we're looking for the largest subset, C of V, where every pair of vertices in C has an edge between them. We call this structure a clique. That's C, right, for clique. So we call this structure we find a clique. You want every vertex to be connected to every other vertex. If you had like 5 vertices, that would be like every pair of vertices connected to each other. There's a connection missing here, connection missing here, and then there's one there. Okay, so there, every pair of vertices is connected. All right. So that's what we're looking for, is a set of vertices where they're all connected to each other. Look at this example. See what the largest set of vertices you can find that are all connected to each other. I'll give you a minute here. Pause the video. Think about it. Well, starting off, we could do one vertex, but that's pretty boring. Already you can see that if you just pick like G and A, these guys are connected to each other. This is a clique of size 2. 2 vertices that are connected to each other completely. All right? Every vertex in that set is connected. Now, kind of in a boring way, because there's only 2 vertices. And you might have stared a little bit longer, and you might have seen, oh, actually A, instead of picking G, we could take like B and C. By taking these guys, we get a clique of size 3, right? All 3 of these vertices are connected to each other. Can we do better than that? Well, yes. Actually, this group right here, this is a clique of size 4, right? take any pair of vertices B, C, D, and F, take any pair inside that set, and they have a line between them. They have a connection, an edge connecting them. Okay? Is there a clique of size 5 anywhere? Well, that would look like this. This is what a clique of size 5 would look like. You can move the vertices around. They don't have to be in this shape. They can be like this guy. You can see I put one of the vertices in the center. Another 4 clique could look like this. So it's not enough to just say, oh, I don't see like that pentagram inside this thing, because actually it could take many different shapes depending on how you move the vertices around. So this is also a clique of size 4. Just shifted the vertices. That said, if you stare at it for a while, you'll see actually there is no clique of size 5. This is as big as it gets. That's our clique. That's our max clique size. Okay? So that's the max. And that's the answer we'd want to produce, is this group of vertices B, C, D, F. That would be the goal of this optimization variant. All right? If there's multiple cliques, by the way, of the same size, any one of them is acceptable. We're not going to be picky. All right? Now, that said, this guy, this clique problem, and you can probably have guessed this, is where we were going, it's also not known to be solvable in less than n times 2 to the n. Yeah, best known algorithm. Is something like that. Actually, it's probably slightly worse, because it'll turn out that this is a trickier variant than the one we're actually going to be considering. So, yeah, best known algorithm to solve cliques. Also exponential time, despite seeming like such a simple problem. You're just looking for a bunch of vertices that are all connected to each other. But somehow this is difficult, right? Or at least it appears to be. Okay? So variance. This is where I want to think about what else could we do to maybe even simplify this problem further. Because the clique problem that we just thought about, that's variant 3. This is the one on the previous page. This is basically from previous page. That guy is fine, but there's some ambiguity. For example, what's the largest clique? You know, what do you do if there's multiple cliques of a certain size? How do you output the clique? You know, all this kinds of stuff. So we could simplify it a little further. Instead of outputting the largest clique, we could just output the integer k, such that the largest clique is of size k. Yeah, so the largest clique has size k elements in it. Now, there's no ambiguity. It should just be a single number. That said, you could even go further. You could go even further to try and reduce the complexity of this problem. You could go down to just a decision problem of whether G, the graph, contains a clique such that the clique size is greater than or equal to k. So this one has an output which is an integer. This outputs an int. This outputs a clique. And this one just outputs a Boolean. Yeah, just outputs a Boolean. Just a yes or a no, a true or a false. And yet, what you're going to find out is this is still exponential time. So we didn't really lose any difficulty. And in fact, if you could solve that first problem in polynomial time, I'm going to prove that all of these problems are solvable in polynomial time, n to a constant, right? Polynomial time meaning good runtime. It's worth mentioning here, there's a huge difference between exponential and polynomial time. You probably already know this, but yeah, that is a significant thing. We're basically saying these two you get for just polynomial additional time. If you can solve this guy in polynomial time, you can use that solution to solve these other two, to leapfrog to them in just polynomial time. This is the hard kind of nugget at the center of the clique problem that we want to focus on. Okay, so let me actually give you those proofs here. First proof, if 1 can be solved in polynomial time, meaning this guy, right? If that guy can be solved in polynomial time, let me prove that 2 can be solved also in polynomial time. Now, I should mention, is a good time to consider pausing the video and trying to prove that yourself, just for practice. See if you can think of a way to solve 2 given a solution to 1. It really will help you if you can brainstorm on this, because the stuff we're going to do in the future is actually kind of similar to this. Okay, and if you want a hint, I will say, think about just brute force. What could you do if you had a solution to 1? What could you do to solve 2? Brute force. Okay, I've assumed you've thought about it. Let me give you the answer. We have a solution to 1, aka we can check whether a particular k has a clique of size of that size that exists. So we can run the algorithm 1 for values k equal to 1, 2, 3, 4, all the way up to the number of vertices. Right, all the way up to a number of vertices. That makes sense, right? So you can run it for each of these guys, and whatever the runtime is of 1, let's say the number of vertices, let's just call this n, and this guy is supposed to run in polynomial time. So this guy has a runtime of n to a constant c, right, where c is a constant. So you can do this for all of those values. Your solution to part 2 is the largest value where this returns true. Return for 2 the largest k where 1 returned true. There you go. That's the solution. One for loop that just runs 1, the solution to 1 that we don't know if it exists. If it existed, though, if that guy existed, just put it in a for loop, run it for all the k values, and then return the largest point at which it was still returning true. Okay? That means the runtime for 2 is going to be in big O of, like the runtime for 1 times we run it n times, right? AKA, if this guy is an n to a constant c, then we're just adding in 1 more copy of n. We're not changing it to exponential, we're just adding in 1 additional copy of n. I realize that's probably off screen. Let me slide that up. You can see it. All right. Okay, with that then, we can then move on to thinking about going from 2 to 3. So if I can solve 1 quickly, I can solve 2 quickly. Now, if we can solve 2, I want to show to you that we can solve 3. Again, feel free to think about this. Think about this for a moment. This one's a little bit trickier, I think, than the previous one, but not too much trickier. The same sort of idea applies. Okay? So, to solve 3, let's just run 2 to find size of largest clique. So we know the size of the largest clique in the graph. Let's just try removing a vertex from the graph. Let's rerun 2 and see if the clique size changes. Right, so we try removing a vertex from the graph, then just run 2 again and see if that changes the size of the clique you found. If you found K before, do we still find K? If we don't find K, that vertex was in the largest clique. Right? This is what I mean. It's a little bit trickier, but not much trickier. So rerun 2 again. Repeat until we find all of the vertices in the clique. In clique. Specifically, I guess I should say, if removing it doesn't change K, restore it. Yeah, so. Or if it does change the clique size, restore it. Restore vertices that change clique size. The idea being, if you do this, if you restore vertices that change the clique size, then when you get done, the only vertices that are left in your graph are literally the ones that are in the clique. If you remove a vertex and you say, ooh, did that change anything? No? Okay. Don't need it. Just toss it away. If we keep doing that all the way down, only adding back in the vertices that change the clique size, we'll end up with exactly those vertices in the clique. Kind of cute, right? Okay. So, the runtime of this, let's think about it. So, removing a vertex from a graph, that's, I guess, a little bit trickier, depending on how you do that, but I'm going to assign that just constant time. We can just check and see if a vertex has been marked as invalid or valid by adding like a boolean to it. That shouldn't be too bad. But if you want to get fussy, you could actually literally make a copy of the graph. It would still end up being polynomial. So the runtime. Didn't give myself enough space here. So the runtime of 3 is going to be in big O of the runtime of 2 times, we need to remove every vertex and then rerun 2. So we're going to do 2 n times. Look familiar? So we just get an extra linear factor. All right, so there you go. For 2 additional linear factors, you can take algorithm 1 and turn it into algorithm 3. These are not claiming to be the most optimal ways to do this, by the way. This is written generically to just make it very simple to see that what we're interested in is going to be decision variance of problems. So I have that down here. Decision variance of problems. So to all the problems we're going to see today, or rather in these sets of notes as we go forward, we're going to be thinking about decision variance because it turns out the optimization variant can generally be solved from the decision variance. Okay, so that's why I state it this way. These are by no means super optimized. They're written this way for clarity of exposition. Hopefully that succeeded and they were clear. That said, so I am going to break the lecture here because this is a long set of lectures. And we will come back next time and think about another simple seeming problem called the independent set problem. So we'll check that out and see what we think about it, and see if maybe we find some similarities to the earlier problems. All right. Thank you so much, folks.